This PowerPoint is on relative motion. So before we start talking about relative motion, we have to talk about a couple of terms. One is a frame of reference, and a frame of reference is a point of view on an event. Now, something interesting about points of view is two different points of view can see the same event as two different things. In class, what I do is I actually do an example where I drop a tennis ball, and in dropping a tennis ball as I'm moving relative to me, the tennis ball will simply drop by the side of my body, so I just see the tennis ball fall straight downward, while relative to the classroom, the students in the classroom see the tennis ball actually while I'm moving forward and dropping the tennis ball, we'll see it move in an arc. So relative to me, the ball goes straight down. Relative to the students in the class, it moves in an arc in a parabola toward the ground. So this diagram shows exactly that. It shows that when an object is dropped, you can see this plane as it drops an object as it's moving forward. The object simply drops down from the plane. So the plane, relative to the plane, it just sees the object drop down. Now, if you're on the outside, what you see is as the plane's going by, the ball will actually make a parabola. It makes an arc as it comes down. All right, and that's the different frames of reference. Those two different frames of reference will see a different motion based on what frame of reference they're in. So in talking about relative motion, in order to change frames of reference from for a motion relative to one perspective to a motion relative to another perspective, you have to do vector addition. And so we've talked about vector addition already. So we have to use vector addition in order to change frames of reference for relative motion. So let's suppose we have a vector that is of one object A relative to another object B. For example, let's say we're talking about a boat that's going down the river. Okay, so the boat moving relative to the water, that would be vector A relative to vector B. But then the water has a motion also. So then there's a vector of the water B relative to the shore, which is C. So the velocity of the water relative to the shore. So that's vector A relative to B, and then vector B relative to C. Now, if I want to figure out the velocity of A relative to C, that is, for our example, the boat relative to the water relative to the shore, if I want to figure out the velocity of the boat relative to the shore, I would need to add those two vectors together. So vector AB plus vector BC will give me vector AC. Now notice the direction of these arrows. Vector A relative to B, vector B relative to C. In order to get vector A relative to C, I have to have those arrows going in the same direction. So A relative to C, A's got to be relative to B first, which is this right here, plus B relative to C, which is this right here, and that gives you the velocity, or I'm sorry, the vector of A relative to C. So let's do an example with this. Let's suppose we have a person who is on a train, and the person is walking relative to the train. So they have a motion, they have a velocity relative to the train. But then the train itself is also moving. So the train has a forward motion, and it's moving relative to the ground. So what would be the velocity of the person relative to the ground? Well, what you would need to do is you need to take the velocity of the person relative to the train and add it to the velocity of the train relative to the ground, and that'll give you the total velocity of the person that they're moving. So notice that the person was moving on the train and the train was moving, so those two velocities will add together to give the total velocity of the person relative to the ground. Now to actually do an example with this, here we have the person that's moving at 4 meters per second relative to the train, and then we got the train that's moving relative to the ground at 21 meters per second. So when we add these two vectors together, we get a total of 25 meters per second with the 4 meters per second plus the 21 meters per second. That gives us 25 meters per second. So with this example, you see that the person's actually going to be moving in the opposite direction of negative 4 meters per second relative to the train. And then the train is still moving at 21 meters per second relative to the ground. So to figure out the velocity of the person relative to the ground, you would take their velocity relative to the train and then the velocity of the train relative to the ground. Now, since the person's moving in the opposite direction, you see that when you add these two together, you get negative 4 plus 21, which gives me a total of 17 meters per second for the person moving relative to the ground. So switching the direction of motion for the person switches the sign so that you have to add the vector with its sign included.
So we have a boat in a stream, and let's suppose this boat is moving at 20 meters per second relative to the water. The current is moving at 10 meters per second relative to the earth. So what I want to know is I want to know how fast the boat is going upstream, and that means how fast it's going when it's going against the current. Then how long does it take to go 600 meters upstream as it's traveling that direction? And then how fast will it be going when it goes back downstream? And then how long will it take to get to 600 meters downstream? So effectively what I'm really looking for is this last question right here. What's the total trip? How long is that total trip around the entire going upstream and then downstream? But I do want to get to these questions also, these other four questions, because what those are going to do is those are going to help me to answer this last question that we have of how long it takes to do the total trip. So let's start with a boat on the stream going upstream, and that means against the current. So if you think about against the current is going to mean that the two vectors are going to be opposing each other. So we have the water relative to the earth moving at 10 meters per second. That's the current. And then we have the boat moving relative to the water. That's going to be 20 meters per second, but it's going to be in the negative direction because it opposes the direction that the stream is going. It opposes the current. So that means it's in the opposite direction. So you're going to add those two vectors together. Now, technically speaking, you may say, well, don't you subtract them? Well, that's partially true, but effectively what you're doing is you're including the direction. That 20 meters per second has a negative in front of it, and that negative just means the direction. So you're technically adding the two vectors. We just have one that has a direction with it. All right. So then you have your two vectors added together, and that's going to give you negative 10 meters per second. Now that negative really doesn't mean anything right now because we're going to be looking for time, and time is a scalar, which doesn't include that negative. So moving on, in order to figure out the time to go upstream, we have to use this equation, velocity equals displacement divided by time, but we're going to rearrange this equation to solve for time. So we bring time over to the other side. That gives us velocity times time equals displacement. And to isolate that time, we got to bring velocity into the denominator on the other side. We get time is going to be equal to displacement divided by velocity. So it's the same equation, just rearranged to solve for time. Then we go ahead and plug in our numbers. 600 meters divided by 10 meters per second. Again, I dropped that direction because it doesn't matter with time. And that's going to give us 60 seconds. So it takes 60 seconds to go upstream with the current being 10 meters per second and the boat being 20 meters per second going against the current. On this next one, let's suppose we go downstream. Now downstream means that the boat is now going with the current. So we have the water relative to the earth, again, is 10 meters per second. This time we have 20 meters per second. It's going to be positive because they're going in the same direction. So then when we add them together, we get a total of 30 meters per second. Now before we figure out the time, I want you to think about how much time is going to pass. Is it going to be more time or less time than it was before? If we're going downstream, are we going to take more time to go downstream than upstream, or is it going to be less time? Well, if you think about it a little bit, with a velocity it's going to be higher, that higher velocity effectively is going to mean that we're going to have less time. So a faster speed, faster velocity means less time as we move forward. All right, so again, our equation, time is going to be equal to displacement divided by velocity. It's going to be equal to 600 divided by 30. That gives us 20 seconds. And then the total time of all of it together is going to be equal to that 60 seconds that it took to go upstream, and then the 20 seconds downstream. That gives me a total of 80 seconds for the round trip.
So in this example, we have a boat that's going on the river, and the boat has a velocity relative to the water. So the boat's velocity relative to the water is in this direction, the northeast direction. But then the water has a velocity also. The velocity of the water relative to the shore is going to be given by this vector right here. Now, something hopefully you notice is that with this velocity northeast, it has an east component that's going to be balanced out by the westward motion of the river, and those two velocities add together will give a resultant that is due north. Now this boat may be pointed northeast, but it's actually going to move north because the eastward component of the velocity is being balanced out by the westward motion of the river. So in looking at this again, in order to find the total velocity, we got the velocity of the boat relative to the water, the velocity of the water relative to the shore, and then we add those together to get the total velocity of the boat relative to the shore. All right, and again, we add them together like vectors to figure out the total velocity of those vectors. So for this example, we have two cars that are driving on the highway. Car 1 is going east at 45 meters per second, and car 2 is going west at 35 meters per second. So the question is, how fast is car 1 moving relative to car 2? Now, if you've ever had experience on the expressway with a car that's coming towards you, hopefully you realize that that car is actually moving faster than it would be if it were sitting still. And that's because the two velocities will add together. Well, if you notice that you got 35 meters per second west and then 45 meters per second east. Now, if you keep those directions, what you're going to end up with is you're going to end up subtracting the two. So this example is basically going to show how these two are actually added to each other to give a total that's greater than either of the two velocities individually. So in our example, we got the first car that has a 45 meter per second velocity relative to the Earth. And then the second car has a 35 meter per second velocity relative to the Earth also. Now, you may notice a problem here. Car 1 is relative to the Earth, and then car 2 is relative to the Earth. Well, in order to determine the total velocity of car 1 relative to car 2, I have to figure out the velocity going this way of the Earth relative to car 2. Now that sounds a little weird because the velocity of the Earth relative to car 2 doesn't make sense. The Earth's not moving, it's the car that's moving. But if you're ever sitting in a car on the expressway, traveling down the expressway at a high rate of speed, you'll see, for example, the guardrail on the side of the road. The guardrail looks like it's going behind you. All right, it's to your side and it's going behind you as it's moving. But technically the guardrail's not moving. You're the one that's moving. But relative to you, the guardrail is moving in the opposite direction. So to determine the velocity of the Earth relative to car 2, all we do is take this vector and literally flip the direction. So to get the total velocity for car 1 to car 2, I have to take the velocity of car 1 to the Earth and then the velocity of the Earth to car 2, which is the opposite of this 35 meters per second. So instead of 35 meters per second west, it's going to be 35 meters per second east. So those two velocities added together will give me the total velocity. So let's look at this example. We got the velocity of the car 1 relative to the Earth of 45 meters per second. Now looking at it again, 35 meters per second of the Earth relative to the car. So notice I switched the direction of 35 meters per second and the Earth moving relative to car 2. Now if you notice, car 2 is actually moving that way, but the Earth looks like it's moving the opposite direction as it's passing by. So the two velocities together, the 45 meters per second and the 35 meters per second, will add together to give a total of 80 meters per second. So the velocity of car 1 relative to car 2 is 80 meters per second. That's why cars always look like they're going faster when they're going toward each other. If two cars are going in the same direction, then they would go, you would subtract the two, or you would actually add the negative, you would add the opposite.